Hey everyone. Second part of structural induction. Let's do induction on binary trees. So I've got here a function size from way back on day 4 that computes the size of a tree, just the number of nodes. And now I'd like to prove that the size of any tree T holding any type is equal to the length of its in-order traversal. Now, that's also true for pre-order or post-order traversals, but let's just do this one because we'll get to use some lemmas that we've defined here and in your homework. Okay, so let's go. Well, first thing I want to note is that here I'm just saying induction directly, which is the same as me having said intros period with no names and then just going. So if you were happy with the names that Cock was going to provide for you, and so long as there's no hypotheses, I think that's pretty fair. Right? Usually we get it right. You can just go straight into induction. I want to comment a little bit on the pattern here. On the left hand side here, we have the pattern for empty. Like all of our other base cases, there's kind of nothing to see. On the right-hand side here, we have the 3 parts and 2 inductive hypotheses. The 3 parts are L, the left subtree of T, when it's a node, V, the value stored in the node T, and R, the right child. Now, L and R are themselves BTXs, which means, in the way induction works on the subparts of a thing, we'll get inductive hypotheses for that. Now, here we have 2 inductive hypotheses because we have 2 subparts, L and R. For lists, there's only one subpart, the tail, so there'll only be one IH. For unary numbers, for nat, well, there's only one subpart in successor, so there'll only be one IH. So now we have 2 IHs. It might seem a little bit intimidating at first, but actually more IHs is better. The more facts you have in your context, the better off you are. The easier it'll be to prove stuff. Solid. What could be bad? Okay, let's do our proofs. Let's look at the subgoals real quick. You can see what our 2 cases are. Empty and node LVR. Okay, that makes sense. The empty case, I feel pretty confident about. In order empty is going to be the empty list, and we're going to get 0 on both sides. But then this will be a little bit more interesting, as you can see from the tactics below. All right, let's see what happens. In the base case, if we wanted to, we could simple first 0, 0, as expected. Okay, this case is more interesting. We have the parts of the tree. We have IHs saying that the property that we're proving, size is equal to the length of an in-order traversal, holds for both of our children, the left subchild and the right one. And then what we have to prove is that our property holds for our whole node, our whole tree right here, so that the size of the whole thing is equal to the length of an in-order traversal of the whole thing. Okay, we'll start by saying, hey, could you simplify just what these functions can do so far? So, okay, here this 1 plus even got turned into an S, and then it's size L plus size R, right? That's the case we saw right up here. Over here, we see that, well, length of that full in-order traversal, this is what an in-order traversal expands to. Length as it is can't reduce anything because it's just an append here. How might we make progress? What could we do next? Well, what about this lemma, app length? App length says, well, the length of one list appended onto another is the sum of their lengths. Here's one list appended onto another. Let's turn it into the sum of their lengths. Okay, great. So now we're making some progress. What do I mean by progress? The right-hand side structure is looking more like the left-hand side structure. Right now they both have a sum of 2 values. That one, we know, okay, well, we know this is going to be exactly the same as size L by IHL. And we know that the length of in order R is going to be the same as size R, but we have a cons to deal with here. But length is defined recursively on its only argument, so a simple here should be able to do some work there. Let's see what it does. Oh, perfect. Right? It basically turns this V into a successor. At this point, you might be able to sort of do a visual match and be like, okay, I've got all my parts in order. I just need to rearrange them. This is a common moment in a lot of cock proofs. You've got everything laid out, and you just have to move it around to be in the right place. What do I mean by laid out? Like, this successor in some sense corresponds to this one. This size L in some sense corresponds to this one by IHL. Sorry, by IHL. And this size R corresponds to length in order R by IHR. So we just need to get our ducks in a row. The first thing we can do is we'll use a lemma that we haven't seen in lecture, but it's one that you'll need to prove on the homework, plus NSM. Critical lemma in part of proving plus com. When we do plus NSM, what it does, let's just see its type, just no need for mystery here. Let me make it bigger. Right? Plus NSM says the successor of n plus m is the same as n plus s of m. It's a way of sort of like undoing a level of successor on the right-hand side. If it's on the left-hand side, simple will do it. But on the right-hand side, you need a lemma to be able to do it. Okay, so plus NSM lets us move this S to the front, which is great. We're starting to match the parts. Okay, now we can use the IH to start setting things up. So by default, Cuck's going to rewrite in a direction that makes it longer. I'm going to rewrite in a direction that maybe makes things shorter. Beautiful. Syntactically equal. So I want to stress here that the only real difference was the shape of hypotheses we got. Everything else kind of flowed the way that everything else has flowed. Structural induction, once you have a handle on sort of straightforward induction on natural numbers, structural induction is just a slight change of the things you're looking at, but the principles I think are exactly the same. I'm going to make one more video after this. There's one more to watch. Just sort of going over an exercise where we're going to be proving the binary functions we defined way back in like day 2 or whatever. We're going to prove some of those correct. All right, I'll see you soon.